Greetings, AP Chemistry students. Today we're going to talk about Le Chatelier's principle and how we can explain changes in the equilibrium position. We've already done quite a bit of work with Le Chatelier's principle, we just haven't called it by this name. But it will help us to explain exactly what's happening when we modify our equilibrium positions. So what Le Chatelier's principle says is that if a stress is applied to a system at equilibrium, the system will shift to minimize that stress. So essentially, whatever you do to disrupt a system from being at equilibrium, it will run in either the forward or the reverse direction until it reestablishes equilibrium. So the first thing you can do is you can change concentration. For instance, if you increase the concentration of a species in the reaction, that would shift your equilibrium towards the other side of the reaction. If you increase the concentration of some of your reactants, if we think about how Q works, that would make Q less than K, and so the reaction would proceed towards the product side to use up those reactants you just added until Q and K are equal again. If you remove a reactant from an equilibrium mixture, then the reaction would run back to the reactant side to try to reform those. If you removed a product, then the reaction is going to proceed towards the product side to try and remake it, because essentially if you remove a product completely from an equilibrium position, then Q is now equal to 0 because one of the products that's in your Q expression is gone. And so the reaction has to proceed to the right in order to make Q equal to K again. Because systems will proceed to equilibrium where Q and K are equal. Pressure. You can modify pressure in 3 different ways. First thing you can do is add or remove a gaseous species. That shifts equilibrium just like concentrations, just like we described on the previous slide. Second thing you could do, you could add an inert gas. You could, for instance, inject some helium or neon or some other gas that does not participate in the reaction. Noble gases will never participate in the reactions. This is a pretty safe bet you can make. That does not affect the concentration, and it does not affect the partial pressures. Therefore, adding an inert gas does nothing to the equilibrium position, but the College Board loves to ask questions about what would happen if you did this, and the answer is it does nothing. And the third thing you could do is change the volume of the container. Changing the volume of the container, you're essentially decreasing the partial pressures of the gases, you're decreasing the total pressures. You're going to cause this reaction to shift to whichever direction will bring the pressure in the container back closer to what it was. So if you squeeze the container into a smaller space, you're increasing the pressure, then the reaction is going to run to whichever side produces fewer moles of gas, so that you're going to bring the pressure in the container back down. If you move it to a larger container and you decrease the pressure, then the reaction is going to run to whichever side produces more gas molecules to bring the pressure back up. Temperature changes the value of K. For an endothermic reaction, heating the reaction up, endothermic delta H is positive, heat is essentially a reactant. Heating the reaction up should result in a shift to the products, and as a result, K would get larger because at your new equilibrium position, you have more products, less reactants. That's a bigger value of K. No surprise for exothermic reactions, ones that produce heat as a product of the reaction, heating the reaction would result in a shift back to the reactant side, and K would decrease. Obviously, if delta H was 0, then changing the temperature would do nothing. If you add a catalyst, that would have no effect on your equilibrium position. It affects your forward and reverse reaction rates equally, and all it does is it helps you establish equilibrium more quickly, but it does not change what the equilibrium position actually is. And then, last but not least, dilution. In other words, if you have a system that's dissolved in water and it's at equilibrium and you dump a bunch of water into the container, that decreases the concentration of all of the soluble species. And so the reaction will shift towards the side with the most dissolved species. Right? So now we're going to look at a few examples of this. All right, so for this reaction, we're going to consider this equilibrium reaction. This is called the Haber process for the synthesis of ammonia. It's one of the most important reactions ever developed, where nitrogen gas reacts with 3 hydrogen gas molecules to produce 2 NH3 gas molecules, and delta H is negative 92 kilojoules per mole. In other words, this reaction is exothermic, so heat is produced in this reaction. So let's consider what would happen under the following scenarios. Let's say you add some nitrogen to the mixture at equilibrium. So first of all, the equilibrium expression says that K equals the concentration of ammonia squared divided by the concentration of nitrogen times the concentration of hydrogen cubed. If you add nitrogen, what you have done is you have made Q smaller. Q is now less than K, so it will shift to the right. Because you have added a bunch of nitrogen, you've made the denominator of the fraction too large, so the reaction needs to shift to the product side to bring everything back into equilibrium. Or from a kinetic standpoint, you could say that by increasing the concentration of nitrogen, you have increased the rate of the forward reaction, so that will result in a shift to the product side. Both explanations are perfectly valid in this case. If you decrease the volume of the container, that would result in a shift to the right, because you have 2 moles of gas versus 4 moles of gas. Because there are 2 moles of gas over here on the reactant side and 2 moles of gas on the product side, 1 plus 3 moles of gas or 4 on the reactant side. So the reaction will shift to the right. It'll make more products. If you increase the temperature, that will result in a shift to the left. And the value of K would decrease. Because essentially heat is like a product, and so by adding heat, this reaction is going to run back to the reactant side where it's endothermic to try to essentially bring the temperature back down, to try and undo what you just did, and so K goes down. If you add argon, which is a noble gas, that has no effect. It would increase the total pressure in your container by adding another gas, but it does not affect any of the partial pressures, so it doesn't do anything. And then if you remove hydrogen, you could say that's going to slow the rate of the forward reaction, or that's going to make Q greater than K, so it would shift to the left. So the real genius of Fritz Haber with developing the Haber process was he was able to develop a way to run this reaction at a fairly low temperature, because adding heat does not make products. It actually forces it away from the products. Although you can't go too cold, because if you think back to kinetics, the rate of the reaction slows down as temperature decreases. And so you need the reaction to still happen at a reasonable rate. So he also added a catalyst. He also developed a way to run this reaction at extremely high pressures to force the reaction to the product side, and developed a way to remove the ammonia from the reaction vessel as it was formed. I believe essentially what he did was he added some water to the reaction vessel, which nitrogen and hydrogen don't dissolve very readily into, but ammonia is super soluble in water, and so that helps to remove it from the vessel. And so it keeps the reaction going towards the product side. So That is the Haber process in a nutshell. Now let's consider one last scenario. If we look at this reaction for the dissociation of ammonium hydroxide, our equilibrium expression would say K equals the concentration of NH4 plus times the concentration of hydroxide divided by the concentration of NH4OH. Now, if we were to have this system at equilibrium and then we added enough water to double the volume of the container, well, what that's going to make happen is Q will now equal the concentration of NH4 plus divided by 2 times the concentration of hydroxide divided by 2 divided by the concentration of NH4OH over 2. We've cut all of these volumes, concentrations in half, but we're having the denominator, but essentially we're cutting the numerator value to a fourth of its original value. So that makes Q is less than K, so it would shift to the right, which goes back to what I said in the notes about if you dilute it, it will shift your equilibrium position to whichever side has the most dissolved species. This is more of a mathematical explanation of this. Because if we're taking half of this value and half of this value, that's essentially multiplying the top by a fourth, and we're multiplying the bottom by a half. So essentially Q is now half of K, and so the reaction would have to shift to the right to reestablish equilibrium. So that is Le Chatelier's principle in a nutshell. If you have some questions about it, there are 3 videos on Le Chatelier's principle in AP Classroom.